Approximately 4.3 light-years away, something fundamental has changed in how we understand our nearest stellar neighbors. The James Webb Space Telescope turned its extraordinary infrared capabilities toward Alpha Centauri and revealed patterns that confirm what theoretical physicists have calculated for decades, but many still hoped observations might somehow contradict. The data doesn't show catastrophe in the dramatic sense. It shows something more permanent. The gravitational and radiative architecture of this triple star system creates conditions that actively prevent stable Earth-like worlds from forming or surviving over the timescales complex chemistry requires. The closest stars to Earth represent not accessible opportunity but a demonstration of how stellar multiplicity destroys planetary habitability through mechanisms no technology can overcome. The problem isn't what Webb found. The problem is what the physics behind those findings implies about proximity, accessibility, and the difference between distance and welcome. Point your attention at any bright star in the southern sky and you're probably looking at photons that left their sources thousands of years ago. Ancient light that departed before human civilization existed and traveled across epochs before reaching your eyes. The universe operates on scales so vast that most stellar distances render human planning horizons meaningless. Just over 4 light-years from Earth exists a triple star system that has occupied a unique place in human imagination precisely because it sits so close. Alpha Centauri represents our nearest stellar neighbors, the closest suns beyond our own. For generations, this proximity seems significant. Perhaps Earth-like worlds orbiting stable stars. Perhaps targets for humanity's first interstellar missions. Perhaps even the possibility of communication with civilizations that evolved under alien suns, close enough that message delays would measure in years rather. Point your attention at any bright star in the southern sky and you're probably looking at photons that left their sources thousands of years ago. Ancient light that departed before human civilization existed and traveled across epochs before reaching your eyes. The universe operates on scales so vast that most stellar distances render human planning horizons meaningless. Just over 4 light-years from Earth exists a triple star system that has occupied a unique place in human imagination precisely because it sits so close. Alpha Centauri represents our nearest stellar neighbors, the closest suns beyond our own. For generations, this proximity seems significant. Perhaps Earth-like worlds orbiting stable stars. Perhaps targets for humanity's first interstellar missions. Perhaps even the possibility of communication with civilizations that evolved under alien suns, close enough that message delays would measure in years rather than millennia. The romantic notion of reaching Alpha Centauri has fueled countless engineering proposals and optimistic speculation. The Breakthrough Starshot initiative proposed sending gram-scale spacecraft at 20% the speed of light specifically because the 4 light-year distance seemed manageable compared to journeys spanning tens or hundreds of light-years to other stellar systems. Mission planners sketched trajectories there because proximity offered the shortest possible interstellar journey, making what remains technologically extraordinary at least conceptually approachable within human lifetimes. When viewers interact with calm, evidence-based space content that focuses on understanding rather than speculation, platforms tend to surface more of it, almost like tuning your recommendations toward clarity instead of manufactured urgency. The James Webb Space Telescope was designed to peer into the earliest epochs of cosmic history. Its 18 gold-plated beryllium mirror segments collect infrared radiation from objects so distant their light has traveled for billions of years. Webb can detect the faint thermal glow of planets forming around young stars and the chemical fingerprints of molecules in distant atmospheres. But Webb can also turn its extraordinary sensitivity toward nearby targets. In recent observations, the telescope examined the Alpha Centauri system with instruments capable of detecting thermal signatures and dust distributions invisible to previous generations of observatories. Webb's observations employed multiple instrument modes optimized for different scientific objectives. The near-infrared camera captured images at wavelengths between 0.6 and 5 microns, revealing the thermal glow of any warm dust orbiting within the habitable zones. The mid-infrared instrument extended this coverage to 28 microns where cooler material farther from the stars emits its peak radiation. Together these instruments mapped the complete thermal environment with sensitivity orders of magnitude beyond any previous observatory. The near-infrared spectrograph provided chemical fingerprinting capabilities that revealed the molecular composition of material in the system. By dispersing incoming light into its component wavelengths, the spectrograph can identify specific molecules through their characteristic absorption and emission features. Water ice, silicate minerals, carbon compounds, and various gases each leave distinctive spectral signatures that Webb can detect and measure. Perhaps most critically, Webb employed coronagraphic modes designed to block the overwhelming glare of the stars themselves. Alpha Centauri A and B are bright enough to saturate Webb's detectors many times over. Without coronagraphic suppression, the stellar light would drown any faint signals from surrounding material. Webb's coronagraphs use precisely shaped masks to block stellar light, while allowing light from nearby regions to pass through. This technique reduced stellar contamination by factors of thousands, enabling detection of faint thermal emission that would otherwise remain invisible. What Webb found should fundamentally alter how we think about our nearest stellar neighbors. The data does not reveal promising signs of stable planetary formation. Instead, it reveals a system locked in perpetual gravitational and radiative warfare where the conditions for building and maintaining habitable worlds may never have existed at all. The Alpha Centauri system is not a single star but three. This basic architectural fact determines everything that follows. Alpha Centauri A and Alpha Centauri B form a binary pair orbiting their common center of mass every 79.9 years. These two stars range from 11.2 astronomical units apart at closest approach to 35.6 astronomical units at maximum separation. 1 astronomical unit equals the distance from Earth to our Sun, approximately 93 million miles. This means that Alpha A and B dance between the orbital distance of Saturn and roughly the distance to the Kuiper belt throughout their 80-year cycle. Alpha Centauri A is a G-type yellow dwarf star, slightly larger and more luminous than our Sun. It burns with approximately 1.5 times solar luminosity, producing a habitable zone that extends from roughly 1 to 2 astronomical units from its surface. Alpha Centauri B is a K-type orange dwarf, smaller and cooler than both our Sun and its primary companion. Its luminosity reaches only about half of solar output, placing its habitable zone closer to the stellar surface at approximately 0.7 to 1.2 astronomical units. The third member of this cosmic family is Proxima Centauri, a red dwarf sitting approximately 13,000 astronomical units from the binary pair. Despite this enormous separation that would take light more than 2 months to cross, Proxima remains gravitationally bound to its larger companions. The three stars form a hierarchical system where the close binary pair orbits each other relatively quickly while Proxima traces an immense orbit requiring perhaps 500,000 to 600,000 years to complete. This architecture matters for one fundamental reason. Triple star systems create gravitational environments so chaotic that stable planetary formation becomes nearly impossible. The mathematics that govern how planets form and survive in such systems reveal a fundamental hostility to the long-term existence of Earth-like worlds. When our solar system formed 4.6 billion years ago, a disk of gas and dust surrounded the young Sun. This protoplanetary disk extended outward for hundreds of astronomical units, containing enough raw material to build the 8 planets we know today plus countless asteroids, comets, and dwarf planets. Slowly, over millions of years, particles within the disk collided and stuck together. Pebbles became boulders through gentle collisions. Boulders became kilometer-scale planetesimals through continued accumulation. Planetesimals became planetary embryos through gravitational attraction. Eventually, 8 major planets emerged from this process, including our rocky Earth orbiting at just the right distance for liquid water to exist on its surface. Single stars like our Sun allow this formation process to unfold without significant gravitational interference. The disk remains coherent throughout the formation period. Orbits stay circular because no external force pulls material into elliptical paths. Timescales measured in millions of years permit the gradual accumulation that builds worlds capable of supporting complex chemistry and perhaps life. But Alpha Centauri A and B are not single stars. They orbit each other at distances that fall within the region where protoplanetary disks should exist. Computer simulations and theoretical models have shown for decades that binary companions truncate protoplanetary disks to a fraction of their potential size. The gravitational pull from a companion star strips away the outer disk material before planets can form from it. Particles that should fall inward and contribute to planet formation are instead scattered into chaotic orbits or ejected entirely from the system. The maximum stable disk radius around each star in a binary system depends critically on the binary separation at closest approach. For Alpha Centauri A and B with their elliptical 80-year orbit, The periastron distance of 11 astronomical units means that stable protoplanetary disks could extend only to approximately 3 to 4 astronomical units from each star. Beyond this distance, gravitational perturbations from the companion would have destroyed any orderly disk structure within thousands of years, far too quickly for planetary formation to proceed. 3 to 4 astronomical units may sound like reasonable space for planetary formation. After all, Earth orbits at 1 astronomical unit, and Mars at 1.5. The habitable zones of both Alpha A and Alpha B fall within this truncation radius, suggesting that terrestrial planets might at least theoretically form in the regions where liquid water could exist. But this truncation creates cascading problems that doom any worlds attempting to form in this hostile environment. First, the truncated disk contains far less material than a full-sized disk around a single star. Estimates suggest that the total disk mass available around each Alpha Centauri component would have been perhaps 1/3 to 1/2 of what surrounded our young Sun. Less material means fewer chances for the random collisions that build larger bodies. The statistical likelihood of forming Earth-mass planets drops dramatically when you start with a fraction of the available building blocks. Second, the outer disk regions that get stripped away represent the reservoir of icy material that delivers water and volatile compounds to inner rocky planets. In our solar system, the asteroid belt and objects from the outer solar system bombarded early Earth with the water that fills our oceans and the organic compounds that seeded primordial chemistry. A truncated disk around Alpha Centauri A or B would possess a diminished reservoir of such delivery mechanisms, leaving any terrestrial planets that form potentially starved of the volatiles necessary for habitability. Third, and most critically, the gravitational perturbations that truncated the disk do not stop once planets form. The same forces that stripped away disk material continue operating on any planetary bodies that emerge from the formation process. This is where the system's hostility transforms from a formation problem into an ongoing survival crisis. Webb's infrared observations have detected thermal signatures in the habitable zones of both Alpha Centauri A and Alpha Centauri B. These signatures tell scientists about dust distribution and temperature profiles in regions where rocky planets might orbit. The instruments can detect warm dust grains heated by stellar radiation and can map their spatial distribution around each star. The data reveals patterns consistent with ongoing gravitational perturbation rather than the smooth, organized structures seen around single stars with stable planetary systems. Around stars with well-ordered planetary systems, dust tends to concentrate in specific zones associated with asteroid belts or debris disks. The patterns show clear structure reflecting the gravitational influence of planets that have carved gaps and concentrated material into rings. Around Alpha Centauri, the patterns appear more diffuse and chaotic. Material seems continuously stirred rather than settled into stable configurations. Every 80 years, Alpha Centauri B sweeps to its closest approach to Alpha Centauri A at 11 astronomical units. During these passages, gravitational forces from the companion tug on any planets orbiting either star. For planets in nearly circular stable orbits, these tugs might seem negligible at first. The gravitational force from a star 11 astronomical units away acting on a planet 1 astronomical unit from its host produces only a tiny perturbation compared to the dominant gravitational pull of the host star itself. But gravitational perturbations accumulate over time. This is the key insight that transforms a seemingly tolerable situation into inevitable destruction. Small orbital changes compound with each passage. A planet that starts in a perfectly circular orbit at 1 astronomical unit from Alpha Centauri A might find its orbit slightly elongated after a few thousand years. The eccentricity increases by a minuscule amount with each 80-year cycle. After a few million years, that elongation could become pronounced. The planet now swings between closer and farther distances from its star, experiencing significant temperature variations throughout its year. After a billion years, the accumulated perturbations could push the planet's orbit to cross those of other bodies in the system or venture into regions where stellar radiation becomes lethal. Computer simulations modeling these dynamics over timescales of billions of years reveal a disturbing pattern. Research groups around the world have run thousands of simulations with varying initial conditions, exploring the full parameter space of possible planetary configurations in the Alpha Centauri system. The results consistently show that the probability of an Earth-like planet in the habitable zone of either star surviving for the full 4.6 billion year age of the system is remarkably low. Numbers vary depending on initial conditions and simulation parameters, but most models show survival probabilities below 30% for planets in optimal orbital configurations. For planets starting in less ideal orbits, perhaps slightly more eccentric or inclined relative to the binary orbital plane, the probability drops towards zero. This brings us to what underlies every discussion of Alpha Centauri habitability. No matter how favorable initial conditions might be, the gravitational architecture of this system ensures that planetary orbits cannot remain stable indefinitely. Worlds that form will eventually be destroyed or ejected. The mathematics is unforgiving and admits no exceptions. The James Webb observations add empirical weight to these theoretical predictions. The dust and thermal signatures Webb detects show a system in ongoing gravitational turmoil, not the calm, organized patterns of mature planetary systems, but the chaotic signatures of material being continuously stirred and redistributed by competing gravitational influences. The infrared data suggests that whatever solid material exists in the habitable zones of these stars does not rest in stable configurations. For decades, astronomers hoped that Alpha Centauri might harbor Earth-like worlds simply because it sits so tantalizingly close. For light years represents the shortest possible interstellar journey. Light from Alpha Centauri to night left that system just over 4 years ago during events still fresh in human memory. Compared to typical astronomical distances spanning thousands or millions of light years, this is nothing, practically next door in cosmic terms. But proximity means nothing if the neighborhood is hostile. The distance to a destination matters only if that destination offers something worth reaching. Alpha Centauri's gravitational environment creates conditions that prevent the very thing we hope to find there: stable, long-lived planetary systems where complex chemistry could unfold over billions of years, worlds where liquid water might persist on surfaces long enough for life to emerge and evolve. These requirements demand orbital stability measured in billions of years, and the Alpha Centauri system cannot provide it. The truncation of protoplanetary disk starves planet formation of raw materials from the beginning. The ongoing gravitational perturbations destabilize any planets that do manage to form. The binary dynamics ensure that over cosmic timescales, nothing survives in the orderly configurations that habitable worlds require. Proxima Centauri sits 13,000 astronomical units from the binary pair. At such enormous distances requiring light more than 2 months to traverse, one might assume its gravitational influence becomes negligible for planetary dynamics near Alpha A or Alpha B. The gravitational force between two masses decreases with the square of distance. At 13,000 astronomical units, surely Proxima exerts only infinitesimal influence on planets orbiting at 1 or 2 astronomical units from Alpha A or Alpha B. The reality is more subtle and more dangerous. Proxima's influence operates on extremely long timescales, but those timescales still matter critically for planetary survival over billions of years. The red dwarf adds another layer of perturbation to the already chaotic binary dynamics, creating a compound destruction mechanism that no stable orbit can escape. Proxima's gravitational pull does not directly affect planets in the inner system with any significant force, but it does affect the orbit of the Alpha A and B binary pair itself. Over timescales of millions of years, Proxima induces slow oscillations in the binary's orbital parameters. The eccentricity of the binary orbit can vary. The orientation of the binary orbital plane can precess. These changes happen gradually, almost imperceptibly on human timescales, but they accumulate over cosmic time. When the binary orbit changes, the gravitational environment experienced by any planets orbiting Alpha A or B also changes. A planet that achieved a marginally stable configuration relative to the current binary orbit may find itself destabilized as the binary parameters drift over millions of years. The narrow windows of stability that theoretical work identifies are not fixed. They shift as Proxima's influence slowly modifies the binary architecture. This is where the full picture of planetary system instability emerges in its complete devastating form. Alpha Centauri is not merely a binary star with formation challenges. It is a triple system where every gravitational interaction compounds every other. The 80-year binary orbit creates medium-term perturbations that accumulate over thousands of orbital cycles. Proxima's immense orbital period creates long-term secular evolution that slowly shifts the architecture of the entire system over cosmic timescales. Planets caught in this gravitational machine face perturbations at multiple frequencies simultaneously. The combination creates orbital evolution so complex that predicting planetary survival beyond certain timescales becomes mathematically intractable. Numerical simulations can track individual planetary orbits for millions or billions of virtual years, but the results are exquisitely sensitive to initial conditions. Tiny differences in starting configurations lead to wildly different outcomes. This sensitivity is a hallmark of chaotic dynamical systems, and it characterizes the Alpha Centauri planetary environment completely. This is the fundamental truth that James Webb observations help confirm through empirical evidence. Our nearest stellar neighbors occupy a gravitational environment so hostile that stable Earth-like worlds may never have formed in the first place. If they somehow formed against the odds, they could not have survived for the billions of years that complex chemistry and life require. The closest potential destination for human exploration or communication harbors not opportunity but catastrophe. In 1687, Isaac Newton published his Principia Mathematica and solved one of the most fundamental problems in physics. Given two bodies attracting each other through gravity, Newton derived equations that perfectly predict their motion forever into the future. Planets orbit stars in elegant ellipses. Moons orbit planets in paths describable by simple mathematical formulas. The equations are elegant, deterministic, and complete. Every position and velocity at any future time can be calculated exactly from initial conditions using nothing more than mathematics. This mathematical triumph created an illusion that the cosmos operates like clockwork. Astronomers in the centuries following Newton predicted eclipses, planetary conjunctions, and comet returns with extraordinary precision. The universe seemed predictable. Physics appeared to offer complete knowledge of gravitational futures to anyone willing to work through the calculations. Then scientists tried to add a third body. The equations became unsolvable. Not merely difficult, not computationally intensive in ways that faster machines might eventually overcome, but fundamentally unsolvable in any general closed form. No finite combination of mathematical functions can describe the motion of three gravitationally interacting bodies for arbitrary initial conditions. The three-body problem has haunted physicists for over 300 years because it reveals something disturbing about gravitational systems that Newton's elegant clockwork universe obscured. The French mathematician Henri Poincaré confronted this impossibility roughly 2 centuries after Newton while competing for a prize offered by King Oscar II of Sweden. His award-winning 1889 memoir revealed something that would eventually birth an entire field of mathematics. He found that three-body gravitational systems exhibit what we now call sensitive dependence on initial conditions. Infinitesimally small differences in starting positions or velocities grow exponentially over time until predictions become meaningless. Poincaré's discovery anticipated chaos theory by nearly a century. He showed that deterministic equations can produce unpredictable behavior. The same laws that allow perfect prediction for two bodies create fundamental unpredictability when three bodies interact. This is not a failure of measurement precision or computational power. It is a mathematical property of the equations themselves. Modern chaos theory formalized Poincaré's insights in the 1960s and 70s. Researchers discovered that chaotic systems possess what they called Lyapunov exponents. These numbers measure how quickly nearby trajectories diverge over time. Positive Lyapunov exponents indicate chaos. The larger the exponent, the faster predictions become unreliable. The Alpha Centauri system possesses strongly positive Lyapunov exponents for any planetary orbits in the habitable zones. Calculations show that orbital predictions lose accuracy by roughly a factor of 10 every few 100,000 years. After a few million years, the uncertainty in predicted orbital positions exceeds the size of the orbit itself. The planet could be anywhere along its path. After a few tens of millions of years, the uncertainty exceeds the size of the entire system. The planet could have been ejected or could have collided with a star. Prediction becomes impossible in principle, not merely in practice. This mathematical chaos explains why even the most sophisticated computer simulations cannot guarantee planetary survival. Researchers can run simulations for billions of virtual years, but the results represent statistical ensembles rather than deterministic predictions. A planet that survives in one simulation may be ejected in another simulation started with positions differing by less than the width of an atom. The chaos is real and irreducible. Alpha Centauri is a three-body system, and the chaos that emerges from its gravitational architecture explains why planetary stability remains permanently beyond reach. No matter what formation conditions existed or what orbital configurations planets might initially achieve, the binary pair's elliptical 80-year orbit creates gravitational conditions that oscillate dramatically throughout each cycle. At periastron, the companion star closes to 11 astronomical units from its partner, creating strong perturbations on any orbiting planets. At apastron, the separation stretches to 36 astronomical units, providing temporary respite. This enormous variation spanning a factor of more than 3 means that planetary environments never achieve equilibrium. But the gravitational chaos is only the beginning of Alpha Centauri's hostility. The mathematics of orbital instability represents just one layer of the system's planetary destruction machinery. What happens in the spaces between these dancing stars involves forces even more immediate and violent than gravitational perturbation. The three bodies of this system do not merely tug on each other through gravity. They also emit radiation and particle winds that create overlapping bombardment zones where no planetary atmosphere can survive indefinitely. Proxima Centauri is where the radiation catastrophe reaches its full destructive potential. This tiny red dwarf possesses only about 12% of the Sun's mass, making it barely massive enough to sustain hydrogen fusion in its core. Red dwarfs represent the most common stellar type in the galaxy, comprising roughly 70% of all stars. Their low mass and luminosity might suggest gentle radiation environments suitable for planetary habitability. The reality involves violent stellar physics that makes red dwarfs among the most hostile stellar environments for nearby planets. Red dwarfs like Proxima Centauri are fully convective. Their low mass creates interior conditions where convection operates from the core all the way to the surface. There is no radiative zone. Hot plasma rising from fusion regions near the center reaches the stellar atmosphere directly. This seemingly minor structural difference has profound consequences for magnetic field generation and stellar activity. Fully convective stars lack the stabilizing boundary layer between radiative and convective regions that exists in stars like our Sun. Their dynamo processes operate throughout the entire stellar volume, creating magnetic fields through turbulent motions at all depths. The resulting magnetic configurations are chaotic and unstable. Field lines become severely tangled and stressed within days or weeks rather than years. When the stored magnetic energy exceeds what the configuration can contain, it releases explosively. These explosive releases are stellar flares. They represent the sudden conversion of stored magnetic energy into radiation, kinetic energy, and accelerated particles. Proxima's flares can increase the star's brightness by factors of hundreds within minutes. A star that normally glows with barely 1,000th of solar luminosity suddenly outputs energy comparable to or exceeding the Sun's steady output. The energy release concentrates heavily in X-ray and extreme ultraviolet wavelengths, creating radiation pulses that would prove lethal to any exposed biology on nearby planets. In 2017, astronomers detected a superflare from Proxima Centauri that demonstrated the extreme violence of red dwarf stellar physics. This single event increased the star's brightness by a factor of approximately 1,000 for roughly 10 seconds. The total energy released exceeded the energy in typical solar flares by factors of thousands. The X-ray and extreme ultraviolet flux during those 10 seconds would have delivered radiation doses to any planet in the habitable zone equivalent to hundreds of years of normal solar exposure compressed into moments. Such superflares would strip atmospheric molecules from rocky planets through multiple mechanisms operating simultaneously. Extreme ultraviolet photons with energies exceeding 20 electron volts can directly ionize atmospheric molecules. The ionized particles gain enough energy to escape planetary gravity entirely, carrying atmospheric mass into space. X-ray photons penetrate deeper into atmospheres, heating gas layers and driving thermal escape processes that accelerate atmospheric loss. Proxima B represents the only confirmed planet in the Alpha Centauri system, and it orbits this violent red dwarf at just 0.048 astronomical units. This tight orbit places Proxima B within the nominal habitable zone where equilibrium temperatures could allow liquid water to exist on the planetary surface. The discovery of Proxima B in 2016 generated tremendous excitement because it suggested that our nearest stellar neighbor might host a potentially habitable world. But calling Proxima B's orbital location habitable ignores the stellar environment entirely, and reveals how misleading the term habitable zone can be when applied without consideration of stellar physics. At 0.048 astronomical units, Proxima B receives stellar wind flux approximately 2,000 times greater than Earth receives from the Sun. Without magnetic protection, atmospheric escape from Proxima B would occur through direct sputtering where stellar wind particles strike the upper atmosphere with energies sufficient to knock atmospheric molecules into escape trajectories. The planet's tight orbit means it is tidally locked to its host star with one hemisphere perpetually facing the star and one perpetually facing away. Tidal locking eliminates the planetary rotation that drives dynamo field generation. Without significant rotation, the liquid core motions that create magnetic fields in planets like Earth cannot develop. Proxima B likely possesses at most a weak remnant magnetic field inadequate to deflect the intense stellar wind bombardment it experiences. Calculations incorporating Proxima's measured stellar wind properties and flare activity suggest that even a substantial initial atmosphere on Proxima B would erode to negligible levels within 100 to 300 million years. This timescale falls far short of the billions of years that complex life required to evolve on Earth. Even if Proxima B formed with an atmosphere 10 times more massive than Earth's current atmosphere, the stellar wind stripping would remove it before biological complexity could emerge. The cumulative evidence points toward Proxima B existing as a desiccated, irradiated world despite its location in the nominal habitable zone. The closest confirmed rocky planet to Earth represents not a promising target for habitability searches but rather a cautionary demonstration of how stellar radiation environments destroy planetary atmospheres. But Proxima's radiation hostility represents only one component of the Alpha Centauri system's atmospheric destruction machinery. The two larger stars, Alpha A and Alpha B, contribute their own particle winds that create additional challenges for any hypothetical planets in the inner system. Alpha Centauri A produces a stellar wind with intensity scaled approximately to its higher luminosity. The wind speed and particle density increase compared to solar values by factors of roughly 1.2 to 1.5. Alpha Centauri B contributes its own stellar wind, weaker than Alpha A's due to its lower luminosity but still significant for planetary atmospheric evolution. In a single star system, either wind would represent manageable challenges for atmospheric retention. Earth maintains its atmosphere against the solar wind through magnetospheric protection combined with atmospheric mass sufficient to resist thermal escape processes. The binary configuration of Alpha A and B transforms manageable challenges into compound destruction. Consider a rocky planet orbiting Alpha Centauri A at 1.2 astronomical units in a hypothetically stable orbit. Throughout most of the 80-year binary cycle, this planet experiences primarily its host star's stellar wind arriving from a consistent direction. As the binary orbit approaches periastron, the companion star Alpha Centauri B closes to 11 astronomical units from Alpha A. The stellar wind from Alpha B now reaches the hypothetical planet from a different direction than the host star's wind. The planet suddenly faces stellar wind bombardment from two directions simultaneously. The interaction between two stellar winds creates physical phenomena far more destructive than simple addition of particle fluxes would suggest. Where the two winds meet, they form shock fronts. As supersonic flows collide, the collision compresses and heats the wind plasma, creating regions of enhanced particle density and temperature. Particles crossing these shock fronts gain energy through acceleration processes that can increase individual particle energies by factors of 10 or more. James Webb spectroscopic observations have detected signatures consistent with these wind interaction processes occurring between Alpha Centauri A and B. The spectral data shows evidence of hot ionized gas in regions between the two main stars, precisely where wind collision should occur. Temperature measurements of this interbinary plasma match theoretical predictions for wind shock heating. The thermal signatures Webb detects indicate plasma temperatures reaching millions of degrees in the wind interaction zones. For hypothetical planets in the Alpha Centauri system, these wind dynamics create cyclically varying atmospheric erosion that accumulates destructively over time. Every 80 years, any atmosphere in the Alpha Centauri system would experience enhanced stripping episodes during periastron passages. Each passage removes additional atmospheric mass through the combined effects of increased wind pressure and shock acceleration. Over millions of years, these periodic losses accumulate to substantial atmospheric erosion, even for planets that might retain atmospheres under steady-state single-star conditions. The cyclic nature of this bombardment creates a ratchet effect where atmospheric mass can only decrease over long timescales. Geological processes might partially replenish atmospheric losses between periastron passages, but cannot keep pace with the periodic stripping events. Each 80-year cycle ends with less atmospheric mass than the previous cycle began with. The radiation and wind challenges extend beyond atmospheric retention on fully formed planets. They reach backward in time to affect the very formation processes that might have produced planets in the first place. Protoplanetary disks consist of gas and dust in a delicate balance between gravitational collapse toward planet formation and dispersal into interstellar space. Stellar radiation heats the disk surface, creating temperature gradients that drive gas escape through photoevaporation. Stellar winds inject momentum that accelerates disk dispersal beyond what radiative heating alone produces. In the Alpha Centauri binary system, the disk dispersal timescale shortens dramatically. Radiation from two stars heats the disk more intensely than radiation from one star. Stellar winds from two directions inject momentum more efficiently than wind from a single direction. The compound effects accelerate disk photoevaporation and dispersal by factors of 2 to 5 compared to single-star systems. A protoplanetary disk around either Alpha Centauri component face dispersal timescales of perhaps 2 to 5 million years rather than the 10 million years available in single-star systems. This shortened formation window dramatically reduced the probability of producing terrestrial planets through core accretion. The truncation effects from gravitational perturbations operated simultaneously with these radiative dispersal effects. The gravitational forces from the companion star stripped outer disk material, while the radiation and wind from both stars accelerated the dispersal of remaining material. James Webb spectroscopic observations have detected chemical signatures consistent with these historical disk dispersal processes. The current dust and gas distributions in the Alpha Centauri system show patterns that match models of binary accelerated disk evolution. The spatial arrangement of remaining solid material suggests that whatever protoplanetary disk once existed dispersed more rapidly than single-star disk models would predict. This brings us to what underlies every discussion of Alpha Centauri habitability. The radiation environment does not merely threaten hypothetical planets that might exist in the system. It actively prevented planets from forming in the first place through accelerated disk dispersal. The planets that did manage to form against these odds emerged into immediate radiation bombardment that began degrading their atmospheres from the moment of formation. The gravitational perturbations destabilize planetary orbits over timescales of hundreds of millions to billions of years. The radiation and stellar wind bombardment strips planetary atmospheres over timescales of tens of millions to hundreds of millions of years. These destruction mechanisms operate on overlapping timescales, ensuring that no formation pathway leads to long-lived habitable conditions. A planet that somehow retained atmosphere against the radiation assault would still face orbital destabilization from gravitational chaos. A planet that somehow achieved orbital stability would still lose its atmosphere to stellar wind stripping. The Alpha Centauri system presents no pathway where both requirements for habitability survive simultaneously. Humanity has always looked to the stars with hope. This impulse predates written language. From ancient Polynesian navigators using stellar patterns to cross thousands of miles of open ocean to medieval astronomers charting planetary motions to modern scientists searching for worlds beyond our solar system, the points of light scattered across the darkness have represented possibility. They have symbolized destinations. Alpha Centauri, sitting just over 4 light-years away, seemed to offer the most accessible possibility of all. The nearest stars beyond our Sun, close enough that communication delays would measure in single-digit years rather than millennia or longer, close enough that interstellar missions could conceivably launch within human planning horizons and return data within human lifetimes. The James Webb Space Telescope's observations have revealed that proximity means nothing when the destination is hostile. Every piece of data Webb has collected points toward the same inescapable conclusion that theoretical models have suggested for decades. Alpha Centauri's worlds, if they exist at all, cannot remain stable long enough to support the complex planetary systems that habitability requires. This conclusion does not emerge from a single observation or a single physical mechanism. It emerges from the convergence of multiple independent lines of evidence, each confirming through different methods and different physical principles that this triple star system represents a gravitational and radiative environment fundamentally unsuitable for Earth-like conditions on any timescale relevant to biological evolution. The gravitational chaos inherent to three-body dynamics ensures that planetary orbits cannot achieve true long-term stability in this system. Computer simulations spanning virtual billions of years consistently show that planets in the habitable zones of either Alpha Centauri A or Alpha Centauri B face ejection or destruction with probabilities exceeding 70% over billion-year timescales. The secular perturbations from the binary companion accumulate inexorably. The influence from distant Proxima shifts the binary parameters over millions of years, closing any temporary stability windows that might have provided refuge. The radiation environment attacks any worlds that might temporarily achieve quasi-stable orbits. 3 stars mean 3 sources of stellar wind and ultraviolet bombardment operating from different directions at different intensities throughout the 80-year binary cycle. Proxima Centauri's violent flare activity creates sterilizing radiation bursts that would destroy exposed biospheres within minutes and strip unprotected atmospheres within geological instants. The binary pair's overlapping stellar wind zones create shock compression and particle acceleration effects that intensify bombardment beyond anything single-star systems experience. The protoplanetary disk truncation starved planetary formation of raw materials from the beginning. Whatever planets formed in this system did so from a fraction of the solid and gaseous material available to planets forming around isolated stars like our Sun. The accelerated disk dispersal from binary radiation further reduced the formation window. Any planets that emerged against these odds were smaller and rarer than they would have been in a more hospitable stellar environment. Each mechanism individually would challenge planetary habitability. Combined, they create compound destruction where no formation pathway leads to worlds capable of supporting complex chemistry over the timescales that life requires. The Proxima B detection in 2016 initially sparked excitement that seemed to validate decades of hoping that our nearest stellar neighbor might host accessible worlds. Here was a confirmed planet orbiting the closest star to our solar system, not a statistical inference, but a genuine planet with measured mass and orbital period occupying what astronomers called the habitable zone of its host star. But as detailed analysis revealed, Proxima B exists as a cautionary tale rather than an encouraging discovery. The planet's tight orbit around its flare-active red dwarf host subjects it to stellar wind bombardment thousands of times more intense than Earth experiences from the Sun. Tidal locking has eliminated the rotation needed to generate protective magnetic fields. The stellar environment strips any atmosphere within geological timescales while periodic superflares sterilize any exposed surface. Proxima B represents not opportunity for humanity but warning about the gap between astronomical terminology and physical habitability. The closest confirmed rocky planet to Earth shows us what happens to worlds that form too close to hostile stars. It demonstrates that proximity to Earth correlates with nothing regarding actual promise as a destination. This revelation carries implications far beyond Alpha Centauri itself. The system serves as a nearby laboratory demonstrating what happens when multiple stars share gravitational territory. Roughly half of stellar systems in our galaxy contain binary or higher-order multiple stars. If gravitational instability prevents stable planetary formation and survival in such systems, then the number of potentially habitable worlds drops significantly from estimates based on single-star systems alone. The universe may be emptier of stable planetary homes than optimistic calculations suggest, and the closest example of this emptiness sits just over 4 light-years away, visible to anyone in the southern hemisphere who looks up at the night sky and dreams of worlds beyond Earth. The James Webb data forces a fundamental reconsideration of what proximity means in an interstellar context. Distance alone tells us nothing about habitability or promise. The gravitational architecture of a stellar system determines whether planets can form and persist far more than the system's distance from Earth. A stable single star 50 light-years away might harbor more promising planetary environments than the chaotic triple system sitting in our cosmic backyard. This reconsideration matters for humanity's interstellar ambitions. Proposals for interstellar probes have long targeted Alpha Centauri precisely because of its proximity. The Breakthrough Starshot initiative proposed sending gram-scale spacecraft at 20% the speed of light with Alpha Centauri as the primary destination. These proposals remain technologically fascinating regardless of what awaits at the destination. The capability to cross interstellar distances represents a milestone in human development worth pursuing for its own sake. But the scientific return from Alpha Centauri missions must be reassessed in light of what we now understand about the system's hostility to stable planetary configurations. Probes arriving at Alpha Centauri after decades of travel will find not Earth-like worlds orbiting stable stars but a gravitationally chaotic triple system where planet formation faced severe handicaps and any planets that formed faced inevitable destruction. The closest stars will demonstrate not the promise of interstellar habitability but the mechanisms of planetary system instability. No matter how advanced human technology becomes, it cannot overcome the fundamental gravitational chaos of three-body systems. We cannot stabilize Alpha Centauri's planetary orbits through any engineering intervention. The masses and separations of the three stars determine the perturbation rates that destabilize any subordinate bodies. No spacecraft, no laser, no technological miracle can change the gravitational constant or rearrange stellar positions to create stability where physics forbids it. We cannot calm Proxima Centauri's flares through external intervention. The convective dynamo processes that generate the tangled magnetic fields responsible for flare activity operate deep within the stellar interior. The stored magnetic energy will continue releasing in violent bursts regardless of anything occurring in the surrounding space. We cannot restore the protoplanetary disk material that was stripped away billions of years ago. The solids and gases that should have built substantial planetary systems in this environment were scattered into interstellar space during the first few million years of the system's existence. That material now drifts among the stars or has been incorporated into other objects far from Alpha Centauri. Physics sets boundaries that engineering cannot cross. This represents not failure of imagination but recognition of constraint. The laws governing gravitational dynamics and stellar physics operate identically throughout the cosmos. They determined outcomes in the Alpha Centauri system 4.6 billion years before humans existed, and they will continue operating regardless of what technologies we develop. Yet this sobering reality also enhances appreciation for what we possess. Earth exists in a single star system with a calm radiation environment featuring a star that lacks the violent flare activity characterizing smaller stellar types. Our planetary system achieves stable orbital configurations that have persisted for over 4 billion years, allowing biological evolution to proceed through the gradual processes that complexity requires. Our world has remained habitable across timescales that would destroy planetary environments in systems like Alpha Centauri. This stability is precious precisely because it proves less common than we assumed. The conditions that permit complex life to emerge and flourish represent not cosmic inevitabilities but fortunate accidents of stellar and planetary configuration. We exist because our star formed alone without gravitationally disruptive companions. We persist because our star burns steadily without the magnetic violence that characterizes convective red dwarfs. We flourish because our planetary system achieved the stability that Alpha Centauri could not provide. Alpha Centauri's hostility transforms how we might view our planetary home, not as one habitable world among countless nearby others but as a precious island of stability in a gravitationally chaotic universe, not as a starting point for easy expansion to accessible neighboring systems, but as a rare oasis that may have few reachable counterparts within any practical interstellar distance. This perspective need not produce despair. Understanding that Earth represents something precious rather than something common provides motivation for protecting what we have rather than assuming we can simply relocate when convenience suggests. The cosmic rarity of stable, habitable environments argues for treating our own environment as the irreplaceable resource it actually is. The dream of Alpha Centauri collapses not because we lack imagination or ambition but because the physics permits no other outcome. Gravitational chaos from three gravitationally interacting stellar masses prevents stable orbits for any subordinate bodies over the timescales that habitability requires. Radiation violence from stellar winds and flares prevents atmospheric retention and surface habitability. Truncated and rapidly dispersed protoplanetary disks prevented substantial planetary formation in the first place. Every mechanism points toward the same conclusion through independent physical pathways that reinforce each other. Our nearest stellar neighbors are not neighbors in any meaningful sense of that word. They are a gravitational combat zone where planetary stability represents a mathematical impossibility rather than a challenging engineering problem. The 4 light-years separating us from Alpha Centauri might as well be 40 light-years or 400 or 4,000 when the destination offers nothing that human ambitions seek. The James Webb Space Telescope has shown us truth where we hope to find promise. The truth is that proximity deceives when divorced from physical conditions. The truth is that stellar multiplicity destroys planetary systems through mechanisms that no technology can overcome. The truth is that the closest stars hide the harshest reality about planetary survival rather than the accessible opportunities we imagined finding there. Alpha Centauri will continue burning in southern hemisphere skies for billions of years to come. The 3 stars will continue their gravitational dance, destabilizing any material that ventures into the contested zones between them. Proxima will continue flaring with violence that would sterilize nearby worlds. The system will remain beautiful to observe and deadly to inhabit. Humanity will continue dreaming of interstellar reach because that impulse lies deep in our nature. We will continue developing technologies that might someday carry probes or people across the gulfs between stars. We will continue searching for destinations worthy of the enormous efforts that interstellar travel demands. But the destination those dreams target must shift to more distant stars where gravitational calm and radiative quiet permit the stable planetary systems that habitability requires. The nearest stars have revealed themselves as hostile. The welcome we imagined finding there never existed. The universe's closest invitation was actually a warning sign written in the language of gravitational dynamics and stellar physics. We have finally learned to read that language. We have received the message. And now, at last, we understand what it means. The stars will always call to humanity. But we must learn to distinguish between calls worth answering and warnings we should heed. Alpha Centauri taught us the difference. That lesson alone justifies every observation that revealed it. Understanding space often means accepting limits, not conquering them. If you found value in this careful examination of what Webb's observations actually reveal about our nearest stellar neighbors, consider subscribing to continue exploring the universe through evidence rather than expectation. The cosmos offers enough genuine mysteries without manufacturing fictional ones.